Hello everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Ruda Adib. I'm a principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Dr. Robin Nisan, followed by a listing of the upcoming webinars in the webinar series. After Robin's opening remarks, we will transition to the technical portion of the webinar. Today's event features two presentations on hexavalent chrome elimination from hard chrome surface finishing. First, Dr. Jonathan McCree will talk about the use of electrodeposited nanostructured alloys for functional and structural applications, followed by a brief Q&A session. Second, Mr. Jack Benfer and Mr. Ruben Prado will talk about electrodeposition of nanocrystalline cobalt phosphorus alloy coating as an alternative to hard chromium electroplating. Their presentation will also be followed by a short Q&A session. We will conclude the webinar with an interactive Q&A session, including both our presenters. Today's broadcast will be listened only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions in advance of the Q&A sessions. With over 100 people on today's call, it is logistically challenging to open all the lines for oral questions. Therefore, the phone lines will remain listen-only throughout the presentation. Here we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen. However, if you continue to have problems, please submit a comment using the chat box that is in the left lower corner of your screen. With that, I would like to introduce Dr. Robin Nisan, who is the SERDP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining SERDP and ESTCP, Robin worked at Navarre's Weapons Division China Lake in California. Turning it over to you, Robin.
Well, thank you very much, Rula. And first of all, thank you everyone for calling in today for our webinar series. We're glad to have you here, and I think we have a very exciting pair of talks to present to you all. So with that, let's give you a brief description of SERDP and ESTCP. SERDP, the Strategic Environmental Research and Development Program, was established in 1991. It is a partnership between DoD, DOE, and EPA. And we are very much requirements driven. We identify high priority environmental S&T investment opportunities that we think will address DoD requirements. We fund advanced technology development as well as fundamental research in environmental areas. ESTCP is the Environmental Security Technology Certification Program. Here we demonstrate innovative, cost-effective, environmental as well as energy technologies. We'd like to capitalize on past investments and transition technologies out of the lab and into the fleet or onto our ranges. We promote implementation and try to facilitate regulatory acceptance. We have 5 program areas, and they are listed on this view graph: energy and water, environmental restoration, munitions response, resource conservation and climate change, as well as weapon systems and platforms. All of these, both SERDP and ESTCP, except for energy and water, which is ESTCP only. As far as weapon systems and platforms go, we have several focus areas, and they include surface engineering and structural materials. We'll hear quite a bit about that today. Also energetic materials and munitions, noise and other emissions, waste reductions and treatment in DoD operations, which I guess is also covered in today's discussions, and lead-free electronics. In the future, we have several webinars coming up. The first one, light-emitting dioding, the way to sophisticated energy-efficient exterior lighting systems for DoD installations, or leading the way, I guess, is probably the way it was meant to be. And then we have one coming up on assessment and treatment of contaminated sediments. That's October 29th. On November 12th, munitions response, land-based program, and on December 3rd, emerging contaminants, fluorochemicals and 1,4-dioxane. And then in the middle of December, December 17th, watershed and stormwater management. So several good topics coming up. If any of these interest you or your colleagues, please sign into the webinar series for us. With that, I'm passing it back to Rula, who will introduce our first speaker.
Wonderful. Thank you, Robin. It is now my pleasure to introduce Dr. Jonathan McCree, who is the Vice President of Research and Development for Integrant Technologies. Dr. McCree received his bachelor's degree in Materials Engineering at Queen's University and his PhD from the Department of Material Science and Engineering from the University of Toronto. He has worked in the area of nanostructured materials for over 17 years with a focus on microstructure property relationships of nanocrystalline materials and the adhesion of nanometal coatings to polymer composites. Dr. McCree has served as a PI for multiple DoD-funded projects. He is active in a number of professional organizations, including the Professional Engineers of Ontario, American Electroplaters and Surface Finishers Society, SAMPE, SAE, and ASM International. And with that, I turn it over to you, Jonathan.
Okay, great. Thank you very much, Rula. First off, I'd like to thank everyone for giving me the opportunity to talk to you about some of the interesting technology that we've developed over the years through the various SERDP and ESTCP projects we've worked on. So the agenda for the presentation is I'll start off with a problem statement, overarching problem statement for the different programs that we worked on. Then I'll move into just a very brief high-level overview of nanostructured materials. And then I'll very briefly talk about the 3 SERDP projects and that we've worked on, which include the cobalt phosphorus for hard chrome replacement, nano-cobalt alloys as alternatives to copper beryllium high-strength bushings, and pulse-plated zinc nickel as an alternative to cadmium plating. And then I'll get some conclusions and move into a question period. So the overarching problem statement that we've worked on, the general theme is to eliminate toxic substances that are used in metal finishing operations throughout the DoD. The first project we worked on was looking at hard chrome replacement. Hard chrome is used for corrosion and wear protection of steel components, such as hydraulics, shocks, and struts. However, the process uses hexavalent chromium, which is a known carcinogen. So there's a high desire to eliminate and find alternative processes. The next project we worked on was looking at an alternative for copper beryllium. Copper beryllium is a high-strength, high-resilience copper alloy. It's used in spring contacts and anti-fretting and anti-galling bushings. However, beryllium is a toxic substance. In this case, the actual metal is the toxic and is the problem, so finding an alternative to the metal. Whereas chrome, as a metal, it's okay, but the process to make it is toxic. And then the last project I'll talk about involves trying to find an alternative for electrodeposited cadmium coatings. Cadmium is also used for corrosion protection of steel. However, it's a sacrificial corrosion protection. And in this case, both the process and the metal are toxic. So before I talk in any detail about the projects, I'll just give you a brief overview of what a nanostructured material is. So when we talk about nanostructured materials, what we're referring to is basically just a metal, but with a very fine grain size. So conventional metals have grain sizes in the range of anywhere between 3, 10, 100 microns. And a nanostructured material is the same thing, but with a grain size in the range of 20 nanometers. And when you reduce the grain size to such a large extent, you have a very high fraction of grain boundaries, and this causes a change to a number of the properties. And one of the biggest changes is related to the strength and the hardness of the material. As an example, with nickel, by decreasing the grain size from 20 microns to 20 nanometers, you get an increase in yield strength from 100 MPa to 900 MPa. So you see very high increases in strength. As well, you see large increases in hardness, in this case from 140 Vickers to about 450 Vickers. On the next slide, it shows an example of the stress-strain curves for a nickel alloy compared to some conventional materials such as titanium, aluminum, and steel. So by decreasing the grain size, you can see that the nanostructure material has much higher ultimate tensile strength, but still has quite a lot of ductility or toughness. So it can be used for structural materials, for structural applications. So how do we achieve these properties? The materials that we work with are made via electrodeposition. And the way we control the microstructure is through pulse electrodeposition. Pulse plating favors nucleation of new grains over growth of existing grains, so it results in an ultrafine grain structure throughout the entire thickness of the coating, right from the interface substrate. So what you'll see in conventional electroplating is right at the interface of where you start plating, you might see a very fine structure, but then as you grow the thickness of the material, you'll start to see the grains elongate and get very columnar, and they'll grow to large sizes. In our nanostructured materials, by pulse plating, as well as through the chemistry of the solutions, we can control this grain size so that you can keep a very fine grain size, about in the order of 20 nanometers or so, right through the thickness. So you get very uniform properties through very large, high thicknesses. The one thing I will mention at this point is, because it often comes up, is that there's no nano-sized particles involved in our process. Through electrodeposition, you deposit metal ions right from basically aqueous form to solid metal at the cathode. And they're arranged in the nanostructures so that you go from ions to solid metal, and it never results in any particles during the manufacturing process. Now the different materials that you can make, nanostructured materials that you can make with these processes, are those that are limited that you can electrodeposit. So at Integran, we've branded those nanometals as Nanovate. So you might see that term come up throughout the presentation. And we have different series. So the N1000 series is the nickel alloys, and those are good, generally used for good hardness and wear and strength and corrosion resistance. An example of where that material is used is putting a thin layer of nickel over a carbon fiber golf shaft. The N2000 series are a nickel alloy, and those have unique properties such as magnetic shielding and low coefficient of thermal expansion through alloying with iron. So those are typically nickel iron alloys with unique properties related to their magnetic properties or the low coefficient of thermal expansion. The R3000 series are the cobalt alloys that I'll go into a little bit in this presentation. And the C4000 series is a high purity fine-grained copper. Another interesting feature of the nanomaterials is that due to their ultrafine grain size, they also possess a number of interesting functional properties in addition to the structural properties. With electrodeposition, you can make these as coating or freestanding structures. So the interesting combination of the structural and the functional properties result in a number of different interesting applications where they can be used. An example of some of the functional properties is with the decrease in grain size, you get excellent wear resistance. You get a lower coefficient of friction. You still get good corrosion, which is largely determined by the composition, but you see a decrease in the localized corrosion attack. Since there's so many grain boundaries, the corrosion activity is spread evenly throughout the whole material and isn't focused on individual point sources as you see in conventional materials where you get severe intergranular attack. They also have interesting catalytic and magnetic properties. So with this, at the beginning of the SERDP projects, we asked, can these nanostructured materials be used as alternatives to the toxic chromium, cadmium, and beryllium containing processes? So that's kind of what started each of the projects that we looked at. So all the three projects that we looked at involved trying to find an alternative for some of the toxic substances. So first off, I'll talk about the nano-cobalt phos for hard chrome alternative, which was covered originally in Pollution Prevention 1152 SERDP project, where we looked at it for replacing steel or chrome coatings on hydraulics, shocks, and etc. The second project involved the WP2137, which was the copper beryllium alternative, and the last project was WP1616, where we looked at for the CAD alternative. So I won't talk in too much detail about the hard chrome alternative project because Jack and Ruben will be going that in quite detail in their presentation about all the work that they've done at Jacksonville during the demonstration validation. I'll just quickly briefly introduce it. So the development started way back in 2000 where it was completely wide open, where we looked at all nanostructured alloys to try to find the best material for chrome replacement. We were limited to try to, at the time, to try to only work with materials that weren't currently on any lists as basically the banned list of substances. So at the time, after the initial development, cobalt was selected as the best fit because it had the best set of properties and environmental acceptability. The positive results of that project then moved the technology basically to the demonstration and validation phase and ultimately to commercialization. So the ESTCP project entered in 2004, and that was the work involved with Jacksonville. And then the process was deployed to Jacksonville in 2006, where it was looked at for validation for various aerospace applications, which included both hard chrome as well as thin dense chrome applications. And it addressed all configurations, so it was suitable for line-of-sight applications as well as non-line-of-sight applications, such as coating the ID of cylinder bores. And then it has also been used commercially. It was licensed to Enduro Industries in 2007. So the main advantages of the Nanovate CR, which is a nanocrystalline cobalt phosphorus alloy as the hard chrome alternative, are the main advantage is the high deposition rate. It's a very fast process, and in fact it's 5 times faster than chrome, which can result in shorter cycle for processing time and increased throughput. It's also very high current efficiency compared to chrome. It's almost over 90% efficient, whereas chrome is only about 20% efficient. Therefore, you get 20 times less process power used in the process. It's also a drop-in technology. Since it is an electroplating process, you can potentially reuse the equipment with minimal training to the staff to use it. And the bath stability is very good. It's a fairly simple chemistry, and it's very robust. In fact, the main process that we've had at Integran has never been replaced since its initial mix-up in 2004. So that's a very good demonstration of its robustness. And I have one slide here on the properties. One of the best properties is related to its corrosion protection compared to hard chrome. So here's a slide that shows the time to red rust for various hard chrome materials compared to the nano-cobalt phosphorus. So you can see with the industrial vendors for hard chrome, you go to about just under 200 hours before you start seeing red rust. And then with a better process at Enduro, you can increase that to about just over 300 hours. But with the nanocobalt phosphorus, you can go well over 1,200 hours. In fact, no red rust was even seen on the sample, and this test was stopped after 1,200 hours. And part of the reason for this good corrosion protection is the fact that the cobalt phosphorus is a pit, pore, and crack-free coating. So it's very dense and there's no cracks. Whereas with chromium, it has good corrosion resistance as a metal, but because of the cracks, you'll see corrosion product kind of seep through the cracks, and eventually the base metal corrodes through the cracks. So now I'll move on to the next project that I'll talk about, which is the SERDP WP2137, which involved the copper-beryllium alternatives. So in this case, copper-beryllium is used in different applications because of its high strength and high stiffness, and it's a good material with good frictional properties, non-gulling and non-sparking for different bushings or spring contacts. And the main drawback, as mentioned previously, is that beryllium is a toxic material. Exposure to beryllium can result in a range of diseases, including lung cancer and chronic beryllium disease. The main exposure of the DoD employees or anyone working with copper beryllium is dusts and fumes as a result of the wearing of the materials, or during manufacturing and fabrication, you'll be exposed to the toxic material. So an environmental alternative is desired. In this project, we actually originally looked at developing a high-strength copper alloy for the material as an alternative. Rather than using precipitation hardening, we wanted to use the ultrafine grain size to try to achieve the same strength properties in copper. However, as we progressed in the project, we realized that copper, even with the grain refinement, it's hard to get to those strengths of copper beryllium. So we opened it up and looked at different materials. And what we ended up with is we found that our electroformed cobalt alloy performed very well as an alternative and had a number of the interesting properties that copper beryllium has. So, it had significantly higher tensile and compressive strength than copper beryllium. It had a low coefficient of friction against various pin materials. It had excellent galling resistance. And it had superior performance in a highly loaded subscale bushing test that we performed. Here's a table that shows some of the mechanical properties of the cobalt alloy compared to copper beryllium and another standard bushing material, which is nickel aluminum bronze. So you can see in compression strength, the nanostructured cobalt alloy has higher strength than the copper beryllium and the nickel aluminum bronze, higher tensile strength, has higher tensile strength, and the modulus elasticity isn't generally changed by the nanostructure, and it's actually the same as the copper beryllium. So for the materials, when we talk about our nanostructured materials as chrome replacement, typically they're thin coatings. Now when we move to bushing materials, we're talking about electroforming. So what the electroforming process involves an interesting manufacturing process in that it can near net shape manufacturing process with a high buy to fly ratio. And it can be cost effective due to the less material required during machining. So an example of the process, the first step would be you coat the material onto a mandrel of about the diameter of the bushings that you want to make. And bushing, typical wall thickness in the bushing is about 1/4 of an inch. The second step would be then you remove the mandrel, so you result in just basically a shell of material or a cylinder, which then can be machined into bushings. Resulting in little waste because you just remove what's on the outside and an effective process. And here's an example of a picture of the subscale bushing test that we performed. On the left, it shows the copper beryllium bushing with a steel pin. And on the right, it shows the nano cobalt alloy bushing with a steel pin. So this test involves loading the sample, loading the pin in the sample. Then the pin is then rotated plus or minus 45 degrees for 100 cycles, after which the load is increased by 500 pounds. This continues up into a load of 10,000 pounds, after which it's finished off for 400 cycles at the maximum load. So in this case, the copper beryllium bushing only made it to about 1,725 cycles before it started to break away, whereas the cobalt alloy material made it up to a full 2,000 cycles, 400 cycles at the 10,000 pounds, and the material is virtually untouched. If you looked at the material before and after the test, it looked pretty much identical, showing the very good performance. We have demonstrated that you can produce a wide range of bushings. This is an example of some of the bushings that we've made, demonstrator pieces. You can see a range of diameters with and without flanges. And in fact, we made up bushings up to about 6 inches diameter to date. So you can go from very small bushings to very large bushings. Okay, the last project that I'll talk about today is the SERDP project WP1616, which this project focused on cadmium, finding seeing if our nanomaterials could be used as a cadmium alternative. Specifically, the project looked at determining whether or not the pulse plating technology could be used with a conventional commercial alkaline zinc-nickel plating system and further improve its performance. When we started this project, there was already quite a lot of work done with the alkaline zinc-nickel system, and it was already emerging as a pretty good alternative to cadmium. So we wanted to see whether or not the pulse plating technology could further improve the performance and potential. So specifically, what we found, pulse plating was able to improve, was able to help refine the grain size, which improved the corrosion, hardness, and coefficient of friction, and the appearance as well. It provided a coating with low porosity and uniform composition, thereby leading to good corrosion resistance. And it consistently passed the hydrogen re-embrittlement test, which is also known as the in-service embrittlement, which is a critical requirement when plating on high-strength steels. Whereas in our testing, we found that the conventional DC plating did not consistently pass this, which I'll go into a little bit more detail in the following slide. So when we look at some of the microstructure comparison, what we found was the form and shiny than the DC zinc nickel, which was dull. Cadmium typically came up as this orange color. And the surface morphology was generally smooth and dense with a fine-grained structure, whereas the DC zinc nickel was rough and porous. When you look at the cross-section, you can see that it's pretty dense and pore-free, whereas the DC process has quite a lot of pores through it, which is similar to the cadmium. One of the other things that we found in this project is we measured the open circuit potential of the materials, the different materials that we produced using different methods, and plotted that against the composition of the alloy, and compared it to that for cadmium as well as that for high-strength steel. So in order for the material to be an effective provide sacrificial corrosion protection, you need to be below, the open circuit potential needs to be below that of high-strength steel. However, you want to be as close to high-strength steel as possible in order to minimize the galvanic couple which can potentially lead to bad re-embrittlement process. So what we generally found in our program is that the alkaline zinc nickel process can produce material in this range, but it's difficult to maintain in the composition range where you have a open circuit potential close to that of cadmium and high strength steel. And what we found was with using pulse plating, it was easier to maintain the composition in this range. And therefore, that was one of the reasons why we thought that the pulse plated material performed better than the DC material, because they were able to maintain the composition such that the open circuit potential of the material was close to that of steel. The other benefit related to the re-embrittlement was so I'm sorry, the slide just doesn't seem to be progressing. There we go. So in addition, one of the reasons that might have influenced the re-embrittlement was the influence of the coating porosity. With the DC plating, you have these pores, so you have these pathways, potential pathways of solution down to the substrate. During the corrosion product, hydrogen is evolved and it can be absorbed into the high strength steel. So in addition to maintaining the composition close to that, in the range such that the open circuit potential is close to that of steel, but still below, the absence of these big pores generally means that you're going to see less ingress of hydrogen to the surface, thereby providing better. So the last slide I have on this just gives an overview of the property comparison between the pulse-plated zinc nickel, the DC zinc nickel, and compared to that of cadmium. So you can see the pulse plating provides a higher strength over the DC. They all had great time to red rust and corrosion performance. The coefficient of friction of the nanomaterial was lower than that of the conventional DC zinc nickel material, and it was similar to that of cadmium. The embrittlement passed on all with the standard hydrogen relief bake. And the re-embrittlement, as I discussed, we got consistent passes with our pulse-plated zinc nickel. We got marginal pass fails where about half would pass, half would fail with the DC zinc nickel. And as well, the cadmium performed very similar to the regular DC alkaline zinc nickel plated samples where half passed and half failed. So moving on to the conclusions, nanostructure materials have been shown to meet and or exceed the properties of hard chrome, copper beryllium, and cadmium with numerous advantages for various applications. The implementation of the various technologies are occurring throughout DoD sites, and they can help reduce the occupational health and safety concerns due to lowering the exposure to the toxic substances. So the stage that we're at now with the different materials, and the next steps is for the hard chrome alternative, which is our Nanovate CR, or the Nanostructured Cobalt Phos. We currently have a mill spec for the material, and the technology is available for licensing. Or from Enduro Industries, or you can, we're happy to talk to you here at Integran and discuss prototype materials as well as low volume manufacturing. For the copper beryllium alternative material, we established the proof of concept in the SERDP program, and now we've submitted a proposal to ESTCP to try to move the technology through to the DEMVAL stage at the depot level. And with the cadmium alternative, we found that the pulse plating technology is applicable to standard alkaline zinc nickel chemistries, and we're happy to discuss it with you, or you can look at the final report for the project. And that concludes, I guess, the talk part, and I'm happy to take any questions at this point.
Thank you, John, for a very informative to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions, John, and the first one is from one of our attendees. What main parameters of pulse generator are needed for your process to work?
The specific pulse parameters we do deem as proprietary because it's kind of a trade secret. It is our technology, but it's a combination of the pulse parameters as well as the solution chemistry. But if you look through the literature for typically pulse plating involves very kind of short on times with off times ranging similar to the pulse height or longer. So typically you just want to have enough of a high strength pulse in order to nucleate those grains with enough relaxing time in order to make sure that the boundary layer can replenish with ions so that you don't just basically get burning of material.
Thanc you, John. Can you please explain how the Nano-COP technology was validated as an environmentally friendly alternative to hard chrome, and since cobalt compounds are also well documented to pose their own environmental safety and occupational health impacts?
Yeah, when we started the project back in 2000, when we did the thorough review of the literature, there was basically no indication that cobalt was on any lists of environmental problems. It was used in cobalt chromoly alloys are used in hip implants. There is no known literature at the time showing any problems. Since then, there's been some reports that cobalt might be hazardous in certain materials, but all the reports that we've seen, it was never conclusive. The cobalt was always tested in combination. Cobalt historically has been used as the binding material in cobalt tungsten carbide drill bits, and a lot of the material or studies released were also involved people who worked at grinding shops that ground cobalt tungsten carbide. Even so, in that case, it was mostly inhalation of fine dusts, which in itself is known to be a problem. For example, wood dust is a known carcinogen. So, we are keeping an eye on it. Cobalt now has on being considered as a possible carcinogen. But when you compare that to other, such as nickel plating processes, which are known, it's been put on some precaution lists, and we're monitoring that as we go to see how that progresses.
Thank you. Can you tell us what the average power of the pulse generator is? And can you describe the required power supply and tell us whether it's commercially available?
Yeah, there's generally, most of the power supplies that they're all commercially available. There's a number of different companies that make power supplies. I think there's PE Power is the pulse plating power supply, Dynatronics. Typically, it just has to generate a pulse. I believe most of them generate pulses between 0.1 milliseconds to 100 milliseconds. The total power that you need in terms of voltage and current it really depends on what you're coating and how large your material is. But yeah, they're commercially available, and I'm sure if you do a quick search, you can find a number of suppliers of different equipment. We've worked closely and used Dynatronics power supplies, and they've worked quite well for us.
Thank you. Prior to coating with your nano material, how is the surface prepared or primed?
With the different materials, so when we coat any material, we use a standard electroplating process. So how you would treat the material is exactly how you would treat the material for plating it with any electrodeposited coating. For example, steels typically go through a pickling step to remove the oxide. For example, aluminum would have to go through a double zincate process. Yeah, so it's exactly how you would electroplate onto any material. The same as if you would be nickel plating, would be the same way as you process the substrate for coating it with nanomaterial.
John, how stable are the plating solutions you described? Do they need to be monitored often?
Yeah, as I mentioned, with the cobalt phosphorus process is very stable. You do monitor the cobalt concentration and the additive concentrations and the pH, but through, for example, when we've been using a cobalt alloy for the electroformed bushings, though in order to build up the wall thickness, you have to coat for about 36 hours, and the solution changes very little in that time. So all of our processes that we've developed are fairly stable. When we're working with the zinc-nickel process, the alkaline zinc-nickel process, as an alloy and you're trying to hit a specific composition, that process is a little more tricky. You have to maintain the nickel and zinc ratio in a certain range, and you have to make sure that some of the other parameters such as buildup of carbonates and whatnot is maintained within a certain limit. But generally the processes are stable.
Great. You briefly mentioned that you looked at nanostructured copper alloys, but they never achieved the desired properties. Was there a reason you didn't look further into precipitation hardening with this?
Yeah, at the time when we were looking at the copper beryllium, or sorry, the copper alloys, we were looking at mainly the grain refinement angle. Once those started to show promise, then we really focused on those rather than the copper alloys, because they seemed at the time to meet all of the objectives that we were aiming for. However, getting further enhancements by precipitation hardening of copper alloys is an angle that could be pursued. We just went a different direction with our project.
Great. Couple more questions before we transition to the second portion of the webinar. What is the current status of zinc-nickel pulse plating? Has it been implemented anywhere?
Well, we had a project, and we, I believe there was when we were talking to Jack and Ruben at JAX, they were interested in the technology. We, as a company at Integran, we don't have a zinc-nickel process here as part of our regular business. So we generated the data as the result, and I think there is interest within various portions of the DoD. And I believe in the final report some of the parameters for pulse plating are there, so it's available to look into further. We're just currently not looking at that ourselves.
All right, and the final question is, what application has most successfully adopted the Nanovate technology as a chrome replacement?
The alloy that we see the most, or the application that we see the most traction with is for hydraulic cylinders. Corrosion protection coating on hydraulic bars and hydraulic cylinders. And we believe this is largely due to both the good sliding wear performance of the material against the various seals that are used as the non-cracked coating. So I believe Jack and Ruben have a lot more detail on some of the materials. But the corrosion protection in those environments is the main reason why it's done so well in those applications.
Great, thank you, John. We have a few more questions for you, but we'll save them till the final Q&A.
Okay.
And we're gonna thank you again. And we're going to transition now to our second presentation, which will be given by Mr. Jack Spencer and Mr. Ruben Fredo. Jack is the Senior Corrosion Engineering Technical Expert and Corrosion Control Program Manager for Navarre in Jacksonville. He has over 26 years of Navarre and NAVSEA engineering experience, and he holds a Bachelor of Science degree in Materials Engineering from Virginia Tech and a Master's degree in Materials Science and Engineering from the University of Florida. Jack has received the Civilian Meritorious Service Award in 2015 for significant contributions to the U.S. Navy. Ruben Prado is a senior inorganic coatings chemist currently working in the Materials Engineering Laboratory, also in Jacksonville, Florida. He is the subject matter expert in electroplating and surface finishing, particularly dealing in corrosion and wear coatings on ferrous and non-ferrous alloys in support of various DoD programs. He has dedicated over 28 years of professional service to the Department of Defense. He was recognized as a NAVAIR Associate Fellow in 2011. And with that, I'd like to turn it over to you, Jack, for the presentation.
Yes, thank you very much. Today's talk is going to be related to how we took a electroplating technology from Integran that John McRae just spoke of and scale that technology up, raise the technology readiness level to one that will be appropriate for an industrial facility, and then to demonstrate that particular technology in the field. So for today's talk, that's what I'll be focusing on. We're also related back to some of the issues as to why we have a need to eliminate hard chrome plating from our industrial facilities, and then discuss at the end briefly some future work that we believe is still required before we can further integrate the technology into the DoD. So I think most of us are quite familiar with hexavalent chromium that have been involved with ESTCP initiatives in the past. But in essence, this material has been a safety risk for many years. But until recently, it has been really just tracked and managed through standard OSH policy, utilizing PPE and other engineering controls. However, in 2009, a DoD directive was released that provided a higher priority to eliminate or remove and minimize the usage of hexavalent chromium. And what we're finding today, now that we're in 2015, is that there's additional costs associated with maintaining these processes in the industrial facility. For a NAVAIR depot in general, the work center decontamination that we perform on an annual basis costs each site roughly $1 million a year. And that's gotten more attention from the command and from others that are looking at chrome elimination from another aspect in addition to worker safety. So what you have here is an illustration of a chrome plating tank, a schematic. And in essence, what are some issues with chrome plating? Obviously, there are some solids that collect in the bottom that we have to manage as hazardous waste. But more importantly, there's hex chrome mist. That's generated during the plating process, which results in exposure that requires higher levels of ventilation requirement, more power associated with moving air across the plating tank, and also scrubber systems that can remove the hex chrome material from the ventilation system so it doesn't enter the outside atmosphere in a plating facility. There's also a great deal of agitation in the plating tank to improve plating quality, and that coupled together along with drag out that occurs from your rinse waters and managing that rinse water waste. There's a great deal of not only cost for treatment but potential exposure that we feel responsible to have to minimize to support our plating facilities and those operators. So in essence, we wanted to integrate this technology into an industrial facility managed by a DoD activity. We were selected as the potential site. This was mainly due to the ability in our facility to actually exercise some modifications that will allow us to install demonstration prototype lines and then work some of the early development with the researchers such as Integran, John McRae and his colleagues. And do that as a priority in addition to our current workload in supporting the facility or fleet operations. The illustration that I have on the slide is one of our industrial artisans that performs electroplating work in our facility. And that's a key example of what we need to learn as we go from a research facility and laboratory efforts into the actual industrial plant. So we rely heavily on their expertise, their feedback when it comes to process improvement. And as part of the project that we were leading for ESTCP, we made sure that they were an integral part of the process as much as possible so that we could validate it correctly both in the field and here at our home site. Now, John did a great job explaining the physics and science behind nanostructured materials. We exploited that in this particular project. To eliminate hard chrome plating, we need to have properties that are equivalent to or better than hard chrome electroplates. And from a material science standpoint, those structural property relationships can be controlled through processing. And that's really what we did in this particular project. So Ruben and I worked together with Intergran and exploited that waveform that John was explaining earlier in his presentation. And we designed a specific pulse pattern that would allow us to have optimum properties for the cobalt phosphorus electroplate. So it does indeed produce a nanocrystalline structure. And as he mentioned in his presentation, that nanocrystalline structure modifies mechanical properties, what helps us compete better with the properties that chrome plating provides us for corrosion and wear. So from a process comparison standpoint, the technique that was utilized was later licensed and branded as Nanovate R3010. You may see in some of the literature that is available with this work NCOP, and that was the generic nanocrystalline cobalt phosphorus acronym that we used. We finally stabilized for a commercially available product, Nanovate R3010. And that's what we are qualifying to our military specification that I'll talk about later. But more importantly, the efficiency of the process is what really interests us. That efficiency is very high. It's close to 100%, which is unheard of in most electroplating processes, as compared to hard chrome plating, which is very poor efficient. That ends up causing two issues. Number one, you generate a tremendous amount of hydrogen gas with low efficiency processes, which make you susceptible in many cases to hydrogen embrittlement failures on high strength steels. So this gives us some assurances that any hydrogen embrittlement effect of the process is at least minimized at the beginning due to its efficiency. But more importantly, the plating rates are extremely rapid. And that was some of the first feedback that we got from our production electroplaters, that they were able to produce coatings in times that would typically take 20 to 30 hours, and we could do that in a single shift, an 8-hour shift. Conservatively, we publicly state that it's 5 times faster or 5x faster, but I would say from a rule of thumb, we were seeing efficiencies upwards to 10 times when it came to plating rates. And why that's important is that a facility could actually replace multiple chrome plating process lines with a fewer number of cobalt phosphorus plating lines, which reduces the footprint and allows for other capabilities. And that really interested us when footprint is very limited in our industrial facilities within NavAir. In addition, chrome plating is one of our top candidates for removal. We just finished an assessment that we performed for ESTCP, chrome plating processing infrastructure at our fleet readiness centers across the nation. Accounts for about 30% of our total usage of hexavalent chromium, and it results in roughly around 25,000 gallons of just infrastructure. Those are plating tanks and rinse tanks across our facilities. So this is our top project that we are trying to implement across site for minimization of hex chrome exposure. In terms of technology integration, what you see on the left bottom that I'll highlight with the arrow is the plating tank in our electroplating facility. It's a relatively small one. That's mainly due to scaling up from a DEMVAL line into a full-scale production line. So this would be considered a demonstration validation line that we currently have. 250-gallon plating tank. A question earlier was how stable is this plating tank? It is extremely stable. We do have a very robust solution analysis program that we use to control the electroplating facility. We analyze these tanks on a biweekly basis. And very infrequently do we have to make additions compared to other electroplating technologies. And in general, that was one of the feedback items that we received from the production department, was how stable that particular process was. The main difference of how we had to integrate the technology was to utilize pulse power supplies. So what you see highlighted now is on the upper level is our original pulse power supply. It is a water-cooled system. It was the power supply that was available at the beginning of our integration effort and was used to power the plating tank. Later in the development, there was a secondary effort to develop lower cost and easier to use and maintain power supplies. The photograph on the bottom is that new generation power supply that we installed. It's air-cooled, much easier to operate, less expensive, and we utilized that for this particular project for our activation tank to prepare our substrates. But eventually, long-term power supplies such as those is what we would use for a scaled-up industrial operation. So like any other technology, as you start to scale up and learn more, you start to understand that there's a lot we don't know about the technology. So our responsibilities was to identify what testing requirements do we really have to better characterize this particular electroplate and be able to determine whether or not it would be suitable for use as an alternative. We designed 24 basic tests, and there were more that were performed early on. But these were the testing categories. In essence, the ones 1 through 6 are basically coating quality. Can you actually electroplate, produce an electroplate that meets our appearance requirements, free of porosity, et cetera, free of defects, that we could actually pass a quality assurance visual check in terms of quality. The remaining ones had to do with mechanical properties, fatigue performance, corrosion performance, hydrogen embrittlement, wear, et cetera. And these particular tests have all been completed. They have been published in a joint test protocol report that has been issued to ESTCP, and that one was recently approved. It should be available. We can talk more about that after the presentation on how to access that particular data set. It's far and beyond what we can present today, so we're going to do a brief overview in the remaining slides of that testing. And then in addition, we went into the field with 3 demonstrations. We tried to choose 3 different environments for the Navy. We have an air system, which is a T-45 aircraft. We had a vehicle that's shipboard. It's a spotting dolly that moves aircraft on carrier deck. That was the lifting pen demonstration. And then a Marine Corps construction vehicle, the M9 ACE, this is a hydraulic cylinder that was electroplated and tested in their field. In terms of properties, corrosion testing was one of the original tests that we performed, and as John mentioned earlier, there is indeed noticeable improvement between corrosion performance of a cobalt phosphorus electroplated steel alloy and hard chrome plated. It's predominantly due to the micro cracking that occurs in hard chrome plating, and in the lower photograph, that's readily observable. How you have defects in the electroplate that are a natural occurrence in chrome plating that result in substrate corrosion. From a photographic standpoint, the appearance of cobalt phosphorus coatings appears to be a corrosion product. This is much more pronounced when you optically photograph it than if you were to visually witness these. This has been documented to be a surface tarnish. It's an oxide of cobalt, and I have later in the presentation some additional work we did to confirm that. What we're indicating in these illustrations to the right of the photographs are whether or not we have iron or base metal exposure from doing an X-ray fluorescence spectrometry test. And we have basically cobalt observable in the upper one, and down below in that spectrum, it's predominantly chrome from hard chrome plating and then iron substrate. To confirm that our results are not artificially affected by an accelerated environment, we then produced a data set utilizing beach exposure testing capability that we have south of Jacksonville at the Kennedy Space Center. These particular witness coupons were tracked by NASA employees for us over a period of 12 months, and reported out every 2 months. And a little bit too much for this particular presentation, but in essence, the summary is we duplicated what occurred in the accelerated testing from the previous slide. This is the chrome-plated coupons after 12 months, and this is the nanostructured cobalt phosphorus coupon set after 12 months. You can witness here that there is some light oxidation. So we returned these samples back to our laboratory and had further analysis performed that we'll discuss later in the presentation. A question was asked earlier about the benefits of this coating system, and we saw that firsthand with some testing that we did with NAVC. These are basically hydraulic cylinders that have been actuated in a corrosive environment. The illustration up top is their actual testing apparatus. These cylinders are cycled. They're cycled 1,000 times. They are then moved into a corrosive environment, which is an artificial salt fog chamber, for 10 days, and then returned to another 1,000 cycles. What we found in this test is that our product, the Nanovate R3010 product, survived 10,000 cycles and 100 days of corrosion exposure with no failure, no leakage, and no failure of the electroplate with exposed base metal corrosion. Hard chrome plating is illustrated here, and those typically failed at 4,000 hours. And in fact, in the study, we repeated the chrome plating experiment in parallel with the existing Nanovate R3010, and those also failed prior to any failure occurring on R3010. And that was quite extreme. It was unexpected. Yes, and again, this particular test was done with very thin coatings, which are needed on these systems. Typically for repair work that we do with aircraft systems, they are a little bit thicker. This was a 1 mil coating system that was used on these cylinders. And this is what led to the ability to dem valve on the M9 ACE. This is an illustration of that particular vehicle, and this is the location of the component. This is the piston rod that was plated, and there's another illustration of that later in the presentation. And finally, as a secondary offshoot, we explored the ability to do large thickness deposits. This was a request from our NAVC participants to evaluate the ability to repair propulsion shafting on the ship side of the Navy. What this wear test that was performed evaluated the R3010, or in this case, in this slide, you see that out of the NCOP coating. And you'll notice here that we were able to obtain 78 thousandths thickness, which is illustrated right here, where you can visually see the coating deposit. Quite interesting, number one, that we can go that thick, and we can also do it quite quickly. And that's what led to us to think about other usages of this technology that we'll show in future work. Oxide characterization. The tarnish effect that I referred to earlier in the presentation is witnessed here again. However, these particular processing coupons were ones that were actually obtained from the beach exposure testing. We wanted to make sure we had natural atmospheric corrosion rather than artificially induced oxides. Those were then examined using photoelectron spectroscopy, XPS. And in essence, you can think of that technique, if you're not familiar with it, as a way to understand the valence bonding of the elements that are identified. And in this particular effort, all that was identified are different oxide states of cobalt, and most particular cobalt as a cobalt oxide and a cobalt-3 oxygen-4 oxide. No evidence was found during these surveys of iron substrate, and so we were able to conclude in this that we do indeed have a natural tarnish that's being formed during atmospheric exposure in a marine environment, and that tarnish may provide beneficial properties. And that's something that we explored later on in the project. To further understand hydraulic systems, we exploited a rig test that one of the manufacturers of hydraulic systems, Messier Dowty, utilizes for qualification. This is a simplistic overview of what we did, but in this particular project we evaluated the piston rods and the internal diameters of the cylinder, and we did so using different surface roughnesses of the electroplate as their ground to final dimensions, and then different seal configurations that might exist on a variety of hydraulic cylinder applications. And as a result of that, this would then go into test. This particular system actuates forward and back, reciprocating, and that's how the cycles were then measured after 20,000 cycles, determining whether or not there was any damage to the electroplate or leaking. And what we found in this particular test for the configurations tested was that we had equal or better performance with the cobalt phosphorus electroplate as compared to hard chrome plating. Fatigue testing is a very interesting area to explore within electroplate technology. It requires a lot of individuals to identify how do you perform the fatigue test. To answer that question, we surveyed a fatigue test protocol through Boeing. Since a lot of our aircraft are manufactured by Boeing, we consider them one of our lead OEMs. And they manufacture the F-18. That is one of our most commonly utilized aircraft in the Navy. The axial fatigue test is one that we can't really go in too much detail in this presentation. There's entirely too much data, so we decided to show one particular curve. This particular curve exhibits the loading levels that you apply a test sample to, and then counting the number of cycles until that exhibit fails. For this particular example, what we're illustrating is 0.03 of an inch of a coating thickness in both hard chrome and the cobalt phosphorus electroplate, and then comparing that to bare metal. This was high strength steel 4340, shot peened, and the testing parameters are also highlighted in the blue box at the lower portion of the screen. We duplicated this test for greater thicknesses, 10 and 20 thousandths, as well as utilizing nickel underplates. So there's a great deal of fatigue data, and that data has a lot of statistical analysis in our test report that was issued. And at the moment now, we are consulting with our structural engineers at the Tucson River to assess this data and determine whether or not additional fatigue testing is required at either different load levels, different frequencies, or different ratios in terms of how much stress is actually relieved during the fatigue test. Field demonstrations, this is really what we were trying to accomplish here in addition to the data set. So what we have is an example of how a T45 component, which is an arresting hook pivot assembly, that's this item right here. This is on the aft side of the aircraft, and the arresting hook or tail hook that's used to grab the carrier arresting wire on carrier landings is then attached to the airframe using this situation, and it resides on this cam face for centering purposes. I have another illustration that shows that a little bit better in the next slide, I believe. So the first step of any plating process is to mask it. In this particular case, we are only going to be electroplating the cam face. This is a thermoplastic elastomer mask that we used. Due to the temperature that this technology operates, conventional waxes that are used in electroplating are not able to be utilized. This particular maskant that we used allowed us to selectively electroplate, although there were reported ease of use issues with this that we're addressing in the future work, and that will be discussed in a few minutes. As we went into the field, this upper photograph will show the back end of a T-45 aircraft. This is the arresting hook, and right at that interface is where the arresting hook meets this cam face. And there's a great deal of loading and wear, both due to vibration in flight and shock loading if the aircraft lands off axis, and the arresting hook has to shift to its side position. So what we've noticed here, this is the cobalt phosphorus demonstration component after 72 arrestments on carrier and 700 flight hours. And we have another illustration at 97 arrestments and just over 800 flight hours. And there's a little bit of wear that's occurring in this face, and this is what we're trying to prevent. With the existing pivot assemblies in chrome plating, this wear area goes to base metal. And once it reaches base metal, that item is rejected and sent back to depot for overhaul. So we're tracking this to determine how long will this particular technology improve performance in the field as compared to chrome plating. And at the moment, we're getting excellent results. These are more like burnished areas. They look like wear, but they're very thin. And at the moment now, from our last update, and we have another one due since it's the end of the FY, we've had over 147 arrestments and 1,000 flight hours. We expect that number to be a little bit higher now that some more time has gone by. From the M9 ACE cylinder that I described earlier, this is a close-up. This particular item was electroplated by Integrand for us. It was too large of an item for us to process in our facility. That was one of the few DEMVAL components that we were unable to produce directly in our plating shop, just due to the size of our plating tank. It was then installed, and this is a picture in the field with the prototype designation. And then it operated in Panama City, and then eventually that vehicle was removed from DEMVAL. The prototype item was removed and it was deployed to the field. No report back from field operators of any negative issue associated with that demonstration. From a technology transfer standpoint, we focus more from the engineering side on documents. So the infrastructure of the facility is one that we can manage through Navy working capital funds, either through a capital improvement program or through other funding avenues. So in terms of the process, we have issued internally a local process specification that controls the specific technology that we have in our demonstration line locally. That's referred to as a LPS. We also developed a military specification that was published last year before the end of the project, Mil Detail 32502. That's the electrodeposition of cobalt phosphorus alloy electroplates. That would be the specification upon technology approval that will be referenced in engineering drawings in order to specify this technology. And then from a service standpoint, Nanovate R3010 would then be qualified to this specification through testing and certification letters. AMS specifications are important. That's a little bit further behind. That's a committee-led event, and we're about 80% through. We have a relatively complete draft, but it has to go through a little bit more approval, review, and voting across different industry sectors before that will actually be an approved specification with a referenceable number. So it's currently B13AA is the project ID on that specification. And as I mentioned earlier, the joint test report, JTR, is complete. All of our data is available. At some point in the future, it should be publicly available and available on the ESTCP website. So from a technology readiness level, these technologies take a long time to develop, and they go through many phases. All that we wanted to illustrate here was the amount of effort that has occurred from the beginning concepts under a SERDP to an original ESTCP 0411, which was responsible for establishing our demonstration line that we have here in Jacksonville. We then did preliminary testing and had to perform some supplemental analysis to control plating quality and to down select optimum plating parameters. And once that phase was complete, we then restarted as a new project, WP0936. And that's the project that you would be searching for in the ESTCP database in the future for some of our technical information. We also had support from Navy sponsors, and NESD under Project 348 was paramount for us to be able to integrate more closely with NAVC representatives on the project, since our particular funded task was focused on air systems. So from a future work standpoint, one of the most important feedback responses we got from production was ease of use when it comes to selective plating. So number one, plating tapes need to be resistant to the high temperature that they're exposed to in the plating tank, which is roughly around 185 degrees Fahrenheit. The plating tapes that are currently available from industry meet the requirement of temperature resistance, but do not meet the requirement of ease of use as compared to conventional platers tapes. So we're asking the manufacturers to take certain plating tape adhesives and apply those to different backing materials so we can generate a higher performing tape for this process. And then finally, thermoplastic materials contain a great deal of solvent and require lacquer cure, which is very time consuming, which is what we used in the demonstrations that I showed earlier. What we prefer is to have a conventional wax. There are waxes available. An example of what we're showing here is a high temperature wax that we received from a company in England. And we've initiated some internal development work on utilizing that wax in the plating process. There's a lot of work to be done on masking complex geometries and being able to control the temperature of the wax, as well as ensuring that the wax itself does not act as a contaminant to the plating process. So more to be done there, but those are the two areas that we're focusing on the most in order to continue operating in a more efficient manner. And then finally, the electroplated and electroformed cobalt alloy bushings is one that really caught our eye recently. And we've been working with Intergram on this concept. And just to kind of echo the need, the T45 component that we are producing for DEMVAL has bushings installed in it. Those bushings require raw material stock in order to manufacture them. And what we found recently is that the raw material stock supply system has logistical issues. We've had numerous occasions where we have 3-month delays in manufacturing a bushing for those components that we're currently overhauling. And we just met today with an engineer from the P3 program that actually identified a component that they had been in delay for 3 years for manufacturing of bushings. So we're interested in electroformed nanostructured bushings as an alternative material from a schedule standpoint at an industrial facility that has a high turnaround tempo requirement. This concept would allow us to then have the raw material stock supplier be us, the plating shop, and then we would supply these materials, these cylinders, to our machine shop to manufacture repair bushings. Repair bushings are government-controlled documents. We have 3 drawings that we're focusing on now. Those are drawings associated with a bushing that has a flanged face, as you see in this illustration here. Other bushings will be straight or countersunk. And so we have buy-in from our local facility for this need, and we plan on utilizing our existing plating tank to further mature the technology, allow us to explore the improvement of selective plating, the use of tapes and maskants, and use this concept as a way to do this as we go through data approval with the hard chrome alternative aspect of this project. So finally, the project was very successful in the field. We did confirm that we have the ability now to eliminate hexavalent chromium from the hard chrome plating process by a direct substitution. That substitution allows us to coat both line of sight and non-line of sight areas of a component. In past technologies that have been implemented as a hard chrome plating alternative, such as HBOF and other thermal spray technologies, those are line of sight. And our remaining workload to transition requires coverage areas beyond the line of sight application area. We did confirm the efficiency that was in the original literature as we developed the project to be between 5x and 10x as compared to hard chrome plating. Corrosion performance well exceeded hard chrome plating. We did find, and I agree with what John McRae mentioned earlier, that it seems to be the best implementation mechanism at the moment into the DoD is through hydraulic actuators that OEM would create in field, and that would give us longer life and less longer mean time between failure. Fatigue testing is a very difficult area. We have mixed results based upon the loading used and the protocol specified. Fatigue testing is going to require a lot more analysis from a statistical standpoint, and perhaps specific fatigue protocols based upon the air program or component being evaluated. More to come on that, but I do believe that fatigue testing is not over yet in terms of generating that data for the engineering community. And finally, as I mentioned earlier, high temperature maskants are required to develop and improve ease of use for this technology. We have a concept on how to do that with some future work and leverage our need for improved turnaround time with bushing manufacturing. And that concludes our portion. What I plan to do is to migrate to speakerphone, so Ruben Prado and myself will be able to field any questions that are offered by the audience.
Thank you, Jack. We have time only for just a few questions. So have you performed a cost-benefit analysis, and are there any financial savings other than the health and safety anticipated from this switch?
So part of our final report, there is a cost-benefit analysis, part of that. There is a savings when it comes to turnaround time efficiencies, but also due to the less energy usage, there's a significant cost savings when it comes to energy utilized in the process. In addition, with eliminating hexavalent chrome, we eliminate the risk of regulatory fines from scrubber systems. So there is the ability to not require wet scrubber systems in the ventilation system, which would reduce the cost of the designs that we currently use to control emissions with hard chrome plating.
Great. Have you received any feedback from end users, such as electroplaters?
Oh yes, if I can say, this is Ruben Prado. The feedback that I have gotten is very well. The only thing basically that I have gotten in terms of the I guess challenges, if you will, with the process is not so much the plating itself. I think it's pretty drop-in friendly, if you will, for those that have existing plating lines and want to stand up a cobalt phos line. I guess the only thing is, except the fact that you would have to install your activation tank, which typically with hard chrome plating, that's done within the tank itself doing reverse current etching. In this case, you would need to have an acid activation tank prior to, simply similar to what you would have with a nickel plating tank line, and that's kind of how you would approach this as well. So for the artisans on the line, it was pretty user friendly. There was nothing there in terms of ramp up learning, other than the fact of just utilizing the power supply interface was the only thing, and even then that was fairly simple. The feedback mainly had to do more of the ability to mask complex geometries, and that was the more challenging part of the process for us, in that having to use high temperature maskings, peelable maskings, and do that correctly so that you wouldn't have any compromise or any plating or leaking from failed masking and that kind of thing, including any kind of organic contamination within the bath. So that was really the main feedback that I got. Other than that, they were fairly pleased with the deposition rates and how uniform the coating was, up to very thick coatings.
Thank you so much. Have you evaluated materials compatibility?
Material compatibility was done two ways. One, through exposure to maintenance fluids that are common in DoD. So we do have a data set that provides information regarding the type of damage that could occur to the coating when exposed to fluids. With basic maintenance fluids that are used in DoD, we found no fluids that were detrimental to the cobalt phosphorus coating as compared to hard chrome. However, the cobalt phosphorus coating is sensitive to exposures to nitric acid and chlorine bleach, and that's highlighted in our final report, whereas chrome plating is resistant to those materials.
Wonderful. Thank you so much. Now, a question that maybe Jack and Ruben, you can take a crack at answering first, but then I'd like John to also weigh in. Now that the Nanovate CR and Nano-COP processes have gone through extensive demonstration and validation and have been qualified for use, do you see, from where you're sitting in DoD and in the commercial field, do you see the technology replacing chrome for all applications?
That is a goal that we have through our Fleet Readiness Center command organization at headquarters. So I'm involved with that group. It's a technology investment team to ensure we integrate in best technologies. This is one that we are tracking due to its ability to mitigate risks with hexavalent chromium. So the technology currently with NavAir is not authorized for general applications. That's the work that we're doing now with this data set and then future data set that we may generate. However, we can authorize it from very specific component applications. And for example, the T45 pivot assembly is one that we can approve locally for a repair and overhaul process. So we do plan on a component approval to include bushings in the future while we're awaiting general approval. It's not until we receive general approval can we eliminate and remove the existing infrastructure from the facility, and that's why that's taking on a higher priority.
Thank you. And Jonathan, can you provide an industry and commercial perspective?
From the industry perspective, I think it could be a very long process to replace it for all applications. Everyone has their own special reason why they like chrome. However, the one application where I can see it progressing quite well is for the hydraulic actuators and rods, and in cases where corrosion resistance and sliding wear against seals is the primary concern. We see that moving quite quickly and quite effectively commercially.
Great. Excellent. Thank you so much. On behalf of SERDP and ESTCP, I would like to thank our speakers today for a very informative presentation. The next webinar is on Thursday, October 15, and will focus on sophisticated and energy-efficient exterior lighting systems for DoD installations. This webinar will feature two presenters, Dr. Saifar Rahman from Virginia Tech and Dr. Satyan Mukherjee, who recently retired from Philips Research. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. These materials will contain links to the reports that all of our speakers referred to today. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you for joining us.